It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Oh, hey. Just playing frisbee with my fiance. Clearly she can't throw. Why don't we try using a different frisbee to help her out? Notice that as the frisbee was coming towards me, there was an apparent change in the frequency where it became higher pitched. And when it's going towards my fiance or away from me, there was an apparent change in the frequency where it was lower pitched. This is called the Doppler effect. When an object approaches you, its apparent change in frequency increases. As it moves away from you, its apparent change in frequency decreases. If you didn't hear that too well, let's try it again with me driving my car and beeping the horn. Good morning, everybody. Welcome to Tibbetts Physics. What is crappin' in? Today, we're going to talk about the Doppler effect. I hope you enjoyed the video of my fiance and myself playing frisbee, as well as her recording me while driving my Prius Prime. Hopefully you noticed as the object went by the camera, either the frisbee or the car, that there's a drop off in the apparent frequency. And that's the Doppler effect. So why don't we define it and just draw a few pictures to represent what it looks like. We can define the Doppler effect as the apparent change in frequency due to the motion of a source. In this case, our source will be sound. Why don't we first look at my car while it's stationary and I'm honking the horn. So our first example is just a stationary object. So while it's stationary, on the other side of my car recording the video is my fiance, so we'll draw her really quick. And I guess we'll give her some blonde hair. Okay, so I'm just sitting there honking my horn. My car is not moving. So if we look at this wave fronts of my horn coming out of my car, oops, we'll do purple. The wave fronts are going to be constant because my car is not moving at all. So the distance in between each wave is going to be exactly the same. Now for this scenario, it turns out that a Prius Prime, its frequency of the horn is 420.3 hertz. Okay, so when the car is not moving, the frequency stays constant. So now let's look at the next scenario where my car is moving towards my fiance. So say moving towards. So here we have the Prius Prime. And then we'll draw my fiance towards the right. We'll put a smiling face on her since it's really cold outside and she didn't want to be out there. Thank you. Okay, so as the car is moving towards my fiance, what's going to happen is that the frequency, the previous wavefronts, are going to get squished together. So even though the car is emitting the same frequency, up front they're going to get squished together because the car is moving towards it. And as we could see, because the wavefronts are closer together, what happens is the apparent frequency increases. So we could say apparent frequency increases. So again, the frequency is, the car, is emitting the same frequency of 420.3 hertz, but because the car is moving towards the wavefronts, they get squished together, which means we can see the wavelengths decrease, and a decrease in the wavelength causes an increase in the frequency. So we can also say the wavelength decreases. The apparent frequency that she heard was 426.8 hertz. So as it was going closer towards her, she heard a higher pitched sound. And then lastly, the car passed her. So this time we'll say moving away. We'll draw the car on the right side. And we'll draw my fiance. Unfortunately, she didn't move out of the way, so she got ran over. But fortunately, she was still recording, so we were able to capture the change in frequency. Sorry. So, if she were able to still hear this, as the car is passing her, the wavefronts are now getting separated farther apart. So the car's horn is emitting a frequency towards the left, but each instant in time the car is moving away from those wavefronts. So what happens is they're going to get farther apart as it moves away from her. And what we could see is because they are farther apart, the apparent change in frequency is going to decrease because the wavelength increases. So we could say apparent frequency decreases. And the wavelength increases. So in this case, it's because the car is moving away from the wavefronts. In this scenario, we were able to capture the recording, and she got 377.1 hertz. So that's the frequency she appeared. We could call that the frequency of the observer. 377.1 hertz. If we compare these two, or these three, sorry, the frequency of the source was 420.3 hertz. When it's moving towards her, it increased to 426.8 hertz. And when it moved away from her, it decreased to 377.1 hertz. Now this doesn't only apply to sound, we can also apply the Doppler effect to light. And if we have a star system moving towards us, we could say that that star's apparent frequency, the light that it's emitting, is going to increase, and when that happens, we say it's blue shifted. Now, we don't actually observe blue light, but what happens as the light is shifted towards the blue end of the spectrum. And the same thing for if a star is moving away from us. The frequency is going to decrease, and we can say that's red shifted. And again, the light doesn't turn red, but it moves towards the red end of the spectrum. All star systems and galaxies are moving away from us, and we can see that by their red shift. However, there's one system that's moving towards us, and that's the Andromeda Galaxy, and again, we could tell based on its blue shift. So that's the Doppler effect in a nutshell. Hope you found this video useful. If you did, please like and subscribe, and I'll see you next time. See ya!